The universe is lying to you about its size. Every star you see at night is not a fixed point at a set distance, but part of a grand cosmic illusion. Our entire understanding of space is built on a shaky foundation, and by the end of this, you will see the night sky in a completely new way. We will uncover how the very fabric of space-time, the light we rely on, and the limits of our own perception conspire to create a false map of the heavens. What if the vast gulfs between galaxies are not empty voids but dynamically changing landscapes? How can a measurement as simple as distance be so profoundly relative? What does it mean for our place in the cosmos if we cannot trust the space between here and there? Are you ready to question the reality of the world above us centuries ago, under a sky untainted by city lights? A Greek thinker named Aristarchus looked up and dared to measure the heavens. His tools were his mind, the geometry of triangles, and the shifting phases of the moon. He reasoned that when the moon appeared exactly half illuminated, a perfect right triangle was formed between the Earth, the moon, and the sun. By measuring the angles, he could calculate their distances. His results were startlingly small by today's standards, but the act itself was revolutionary. For the first time, humanity had a method, a logical system to replace pure myth with measurement. This was the birth of cosmic cartography, a first attempt to draw a map of the universe. Yet this brilliant approach was built on a quiet assumption that space itself was a static, unchanging stage. Distances were thought to be absolute and fixed, simple lines you could draw on a cosmic blueprint. This idea of a rigid Euclidean universe where parallel lines never meet and triangles always obey simple rules would become the bedrock of astronomy for nearly 2,000 years. We inherited this model of a fixed and absolute cosmos, a clockwork universe where every object had its designated place. But what if the stage itself is not rigid? What if the very canvas of space can stretch and warp? The ingenuity of those early astronomers is undeniable, but their foundational assumptions, born from the limits of their perception, set the stage for a much grander and more unsettling truth to eventually reveal itself. That quiet assumption of a fixed stage would hold for centuries until a new geometric trick was perfected, one that finally gave us a real, tangible step into the stars. We call it parallax. You experience this effect every day. Hold up a finger and close one eye, then switch eyes. Your finger seems to jump back and forth against the background. This simple shift in perspective is the key to measuring the universe. Astronomers realized they could use the entire orbit of the Earth as their two viewing positions. They would observe a single star, then wait 6 months for our planet to travel to the opposite side of its journey around the Sun, and observe it again. The tiny apparent wiggle of that star against the backdrop of infinitely more distant stars created a colossal triangle in space, with the Earth's orbit as its base. Using trigonometry, the same math used to survey land, they could calculate the star's distance. The results were humbling. The nearest stars were not just a little farther than the Sun, they were almost unthinkably remote, separated by voids measured in light years. This was our first true encounter with the sheer scale of the cosmos. Yet for all its power, parallax introduced a new kind of limit. It created a horizon of measurement. For stars beyond a certain distance, the apparent shift becomes so infinitesimally small that it vanishes into the blur of a telescope's capabilities. It is like trying to see a coin shift from one side of a continent to the other. This geometric method, our first reliable yardstick, only reaches so far. Beyond this parallax horizon, the direct, simple measurement of distance fails us completely, and we are forced to rely on something far less certain, a chain of assumptions and proxies that begins to warp our map of reality. So we are left staring into the darkness beyond our geometric reach, forced to find a new kind of ruler. Astronomers turn to light itself, not its geometry, but its intensity. They searched for what they called standard candles, celestial objects with a known, fixed intrinsic brightness. The idea is beautifully simple. If you know how bright a light bulb truly is, you can tell how far away it is by how dim it appears. A distant city at night is not faint because its lights are weak, but because its light has spread out and diluted across a vast distance to reach your eyes. This inverse square law, where brightness fades with the square of the distance, became our new cosmic tape measure. Two objects became crucial in this endeavor. The first are Cepheids variable stars, old giant stars that pulse rhythmically, growing brighter and dimmer over days or weeks. In the early 1900s, Henrietta Leavitt discovered that the speed of this pulse is directly tied to the star's true power. A slow, languid pulse means an incredibly brilliant star, while a rapid flicker indicates a fainter one. By simply clocking the pulse, we know the bulb's true wattage. The second, even more powerful standard candle is the Type Ia supernova. These are the thermonuclear explosions of white dwarf stars, and they are thought to always explode at nearly the same critical mass. This means they should all reach roughly the same phenomenal peak brightness, outshining entire galaxies for a few glorious weeks. They become mileposts visible across billions of light years. With these tools, we could finally map the grand structure of the universe, measuring the distances to far-off galaxies and revealing the large-scale cosmic web. But this method carries a profound and hidden fragility. It rests entirely on an assumption of uniformity. We must assume that a Cepheid star in a nearby galaxy is identical in its pulse-to-brightness relationship to one in our own. We must believe that every single white dwarf explodes in exactly the same way, with the same pristine purity, regardless of its age or the composition of the star that birthed it. What if that is not true? What if some of these standard candles are manufactured with slight variations, like bulbs from different factories? A candle that is slightly brighter than we assume would make us think it is closer than it truly is. A supernova that is intrinsically fainter would be placed much farther away, distorting our entire three-dimensional map of the cosmos. This is the conundrum. Our entire perception of the universe's vast architecture, the very distances to the galaxies that paint the deep field, hinges on the trustworthiness of these flickering lights. We are left to wonder if the light traveling for millions of years to reach our telescopes is a faithful messenger or a deceptive guide leading us astray in an ocean of space. This chain of trust in flickering lights was shattered by a discovery that redefined reality itself. Edwin Hubble, peering through the Great Telescope at Mount Wilson, noticed something peculiar about the faint smudges of light we now know as other galaxies. Nearly all of them were flying away from us, and the more distant a galaxy was, according to those very standard candles, the faster it was receding. This was not a collection of objects randomly flying apart through a static void. The entire cosmos was growing. The universe itself was expanding. Think of the surface of a balloon as it is being inflated. Glue a few paper dots onto the rubber. As you blow air into the balloon, every dot moves away from every other dot. No single dot is the center of the expansion. The fabric between all of them is simply stretching. This is what is happening to the space between galaxies. The galaxies are not racing through space. They are largely stationary within their local space, but the space itself is stretching, carrying them apart like raisins in a rising loaf of bread. This changes everything about distance. The gap between two galaxies is not a fixed number. It is a number that increases with every passing second. So when we say a galaxy is 1 billion light-years away, we must ask a new and strange question. When do we mean the distance the light traveled to get here, a journey that began 1 billion years ago? Or do we mean the distance to that galaxy right now, which, after a billion years of cosmic expansion, is actually much, much farther away? This is the difference between what astronomers call comoving distance and proper distance. The comoving distance is like the address of the galaxy, a fixed coordinate in the expanding grid. The proper distance is the actual, physical span you would measure with a hypothetical ruler at this very moment, a span that is constantly growing. There is no single, true distance. The measurement you get depends entirely on when you decide to take it. The very idea of a fixed location, a stable here and a stable there, evaporates in this dynamic continuum. The cosmos is not a map hanging on a wall. It is a living, breathing entity, and the space between stars is its stretching skin. This stretching of space does something strange to the light traveling through it. As a galaxy recedes from us, carried away by the expanding fabric of the cosmos, the light waves it emits are physically stretched out on their long journey to our telescopes. Imagine a runner on a moving walkway that is constantly lengthening. Each stride they take becomes longer and more drawn out by the time it reaches the end. In the same way, the light from a distant galaxy arrives stretched, its wavelength now longer than when it began. We see this as a shift toward the red end of the spectrum, a phenomenon we call cosmological redshift. This redshift became our most powerful tool for mapping the universe. By measuring how red a galaxy's light appears, we can deduce how much the universe has expanded since that light was emitted, which in turn tells us its distance. It seems like a perfect cosmic speedometer and odometer combined, but this elegant signal is not as pure as it seems. Galaxies are not just passive passengers on the cosmic expansion. They also have their own local motions, called peculiar velocities, as they dance to the tune of their local gravitational fields. A galaxy might be moving toward us through space even as the space between us expands, or moving away faster than the expansion alone would cause. This creates a Doppler shift, the same effect that makes a siren's pitch drop as an ambulance races past you, that is superimposed on the cosmological redshift. We see the combined effect, a contaminated signal. Is the redness we measure due to the grand expansion of the universe, or simply because that particular galaxy is hurtling away from us at high speed? Untangling this requires complex models and assumptions, and any error directly warps our perceived map of the cosmos. The complications do not end there. We now know the universe's expansion is not steady, it is accelerating. This means the relationship between redshift and distance is not a simple, straight line. The light from the most ancient, distant galaxies has been stretched by an expansion history that was slower in the past and faster now. Their redshift encodes not just a distance, but the entire history of cosmic acceleration during their journey. A single shade of red can correspond to vastly different distances depending on the underlying model of dark energy. So when we point our telescopes at a faint, red speck in the void, we are not seeing a simple postmark from a fixed location. We are reading a complex, layered message. It is a palimpsest written over by local motion, etched by the steady stretch of space, and then rewritten again by the ghostly influence of whatever force is accelerating everything. The color of the light is a profound deception, a single number that tries to tell a billion-year story all at once. But this warping of light is not the final layer of cosmic deception. The very emptiness we perceive between galaxies is not truly empty at all. It is filled with a ghostly presence, an energy inherent to space itself that pushes the universe apart. We call this dark energy, and its discovery revealed that the expansion of the cosmos is not slowing down, as everyone expected, but speeding up. This acceleration stretches the very meaning of distance to its breaking point. There are objects whose light has been traveling toward us for so long that the space between us has expanded faster than the light can cross it. The light from these galaxies is like a runner on a treadmill set to an ever-increasing speed, struggling to make forward progress. We will never see the light they are emitting today because the space it must traverse is stretching faster than its photons can advance. They have passed beyond our cosmic event horizon, forever receding from our view. This creates a fundamental limit to the observable universe, a bubble of reality beyond which we can never know anything. The distance to that horizon is not a fixed number on a map. It is a moving finish line dictated by the relentless push of dark energy. It means the universe accessible to us is finite and shrinking in terms of the number of galaxies we will ever be able to see. The vastness we perceive is only a fraction of what truly exists, a shrinking island in an infinite, unknowable sea. The grand illusion is not just that distances are relative, but that our entire view of the cosmos is temporary and incomplete, a fleeting snapshot of a reality that is forever pulling away from us. This ultimate horizon is painted across the entire sky in the faintest possible light, a ghostly afterglow from the birth of the cosmos itself. We call this the cosmic microwave background radiation. It is the oldest light we can ever see, released when the universe was a mere 380,000 years old, a hot, dense fog of particles that finally cleared enough for light to travel freely. Every direction we look, we see this wall of ancient light. It is the final, fundamental boundary of our observable universe. This is not a boundary in space, but a boundary in time. We cannot see any further not because our telescopes are too weak, but because light from any event before this moment has been scattered and lost to the primordial fog, and light from regions beyond this shell has simply not had enough time in the entire history of the universe to reach us. The distance to this background glow is our absolute cosmic horizon. It defines a bubble, a sphere of visibility centered on us, and here is the profound implication of that bubble. Every observer in the universe, on any planet around any star, has their own unique bubble, their own observable universe with themselves at the center. There is no privileged vantage point. Your here is just as central as my here. This horizon, however, does not represent the edge of all that exists. The universe itself may very well be infinite, stretching on forever beyond that wall of ancient light. We have no way of knowing. The space, the galaxies, the stars beyond our horizon are forever hidden from our view, not because they are not there, but because their light is still in transit, racing across a gulf that is expanding faster than the light can close it. They are like ships that have sailed over the curvature of the Earth, vanished from sight but still very much present. This means any map of cosmic distances we can ever create, no matter how advanced our technology becomes, is fundamentally and permanently incomplete. It is a chart of our local cosmic neighborhood, a single island in an archipelago that may stretch into infinity. We are forever drawing the coastlines of our own limited perception, mistaking the edge of our sight for the edge of the world. So this brings us to the heart of the illusion, a truth that rewrites our understanding of both space and time. The universe is not a three-dimensional stage where events simply happen. In Einstein's theory of relativity, space and time are fused into a single, inseparable fabric called spacetime. You cannot talk about distance without also talking about duration. The very unit we use for cosmic measurement, the light year, screams this truth. A light year is not just a vast distance, it is a story of a journey. It is the distance that a beam of light, traveling at the universe's ultimate speed limit, covers over the course of one full year. When you look at the star Sirius, just over 8 light-years away, you are not seeing Sirius as it is tonight. You are seeing it as it was 8 years ago. The photons striking your retina left that star around the time you were living a different chapter of your life. Every measurement of distance is simultaneously a measurement of time. This fusion creates a profound uncertainty. We can know where a galaxy was, but we can never know where it is. Its present location is a phantom, forever hidden from us. By the time its light reaches us, the galaxy has moved, carried by the cosmic expansion for millions or billions of years. The Andromeda Galaxy, on a collision course with our Milky Way, is 2.5 million light-years away. We see its beautiful spiral structure as it was when early humans were first walking the Earth. But where is Andromeda right now, at this very second? It is not in the place we see. It is vastly closer, already well into its long fall toward us. Our cosmic map is not a snapshot of the present. It is a layered historical archive. The farther you look, the deeper into the past you see. The most distant galaxies are not just far away in space, they are windows to the universe's infancy. The line between where something is and when it existed has been completely erased. We are not just map readers, we are time travelers, staring at a sky full of ghosts and wondering where they have gone. This final layer of cosmic deception strikes at the very heart of our experience of reality. Einstein's theory of relativity did more than just fuse space and time. It shattered the idea of a single, universal present. The concept of now is not a fixed moment that sweeps across the cosmos. It is relative. Two events that appear to happen at the exact same instant for you might occur at completely different times for someone else moving at a different velocity. Imagine a flash of light occurring at the exact center of a moving train car. For a passenger sitting inside the car, the light reaches the front and the back walls simultaneously. But for an observer standing on the platform as the train speeds by, the situation is different. Because the train is moving, the back of the car is rushing toward the point where the flash happened, while the front is moving away from it. From this outside perspective, the light hits the back wall first, and the front wall a fraction of a second later. The very definition of at the same time has been broken. Neither observer is wrong. They are simply experiencing reality from different frames of reference. Now, scale this up to the cosmic level. When we look at the night sky, we see a tapestry of events we perceive as happening simultaneously. A supernova explodes in one galaxy, a star is born in another. We naturally assume these events are occurring in the same present moment that we are living in. But this is the grandest illusion of all. The light from those events has traveled for millions of years to reach us, meaning we are seeing them as they were in the distant past. More profoundly, an alien astronomer on a planet orbiting a star in that supernova's galaxy, moving at a vastly different velocity relative to us, would not agree on what now means. Their present moment would include events in our solar system that we perceive as still far in our future. There is no universal clock ticking away in the background of the cosmos. This relativism makes the very idea of a fixed distance between two cosmic events almost meaningless. To ask how far apart two supernovae are is to ask a question that has no single answer. The separation you measure depends entirely on your state of motion. Your cosmic map, the one you think you are looking at, is not a static snapshot. It is a fluid, dynamic, and deeply personal construct. It is a map drawn not just from a single point in space, but from a single, fleeting frame of reference in the flowing river of spacetime. We are not just looking at a historical archive, we are each composing our own unique version of the present, a version that no other observer in the universe will ever share exactly. This accelerating expansion has a startling consequence for the very nature of reality. Distances are not just growing, they are growing faster and faster. Think of it like a car that is not just cruising down a highway, but pressing its accelerator pedal to the floor. The space between galaxy clusters is the highway, and it is stretching at an ever-increasing rate. This means that the cosmic map we construct today is not just outdated, it is actively becoming obsolete even as we draw it. The gap between two galaxies that we measure as 1 billion light-years wide is, at this very moment, widening at a speed that is itself increasing. The number we assign to their separation is only a temporary label for a relationship in constant, accelerating flux. This bizarre behavior is attributed to the most mysterious substance in the cosmos, dark energy. We do not know what it is. We only see its effect, a kind of anti-gravity that pushes the universe apart. It appears to be an intrinsic property of space itself. The emptier space becomes as galaxies fly away from each other, the more of this repulsive energy seems to exist, driving the expansion ever faster. This means the vacuum of space is not a passive nothingness. It is dynamically active, a simmering sea of energy that is relentlessly stretching the fabric of everything. So when we gaze at the void between stars, we are not looking at a simple, empty gap. We are looking at the engine of cosmic change. This force directly warps our perception of distance. Our brains and our classical physics are wired for a stable, Euclidean world. We intuitively believe that the space between 2 points is a fixed quantity, like the length of a wooden ruler. But dark energy tells us that the ruler itself is made of stretching rubber. The cosmic distances we read about are not the true, current separations. They are a record of how things were when the light began its journey, combined with a complex calculation of how much stretching has occurred since then. The vast gulfs we see in telescope images are an illusion, a fossilized imprint of a past arrangement of galaxies, not a live view of their current positions. The universe is not simply large, it is becoming vaster in a way that fundamentally alters our connection to it. This quantum foam forces us to confront a startling possibility. The very grid of spacetime, the smooth canvas upon which we plot our cosmic distances, might be an illusion of scale, just as a calm ocean appears as a flat, continuous surface from an airplane, but is revealed from a few inches away as a churning chaos of waves and molecules. Spacetime itself may have a fundamental graininess. At the unimaginably tiny scale of the Planck length, a distance so small that 1 trillion of them could fit across a single proton, the serene continuum of Einstein's relativity breaks down. Here, the principles of quantum mechanics reign, where uncertainty and probability are the laws of nature. In this realm, empty space is not empty. It is a seething, turbulent ocean of virtual particles popping in and out of existence, borrowing energy from the vacuum for fleeting moments before vanishing again. This ceaseless activity gives the fabric of reality a foamy, probabilistic texture. Distances at this scale are not fixed, they fluctuate. If you could somehow measure the gap between 2 points separated by a single Planck length, your measurement would yield a different result each time you tried. The concept of a definitive, precise length simply evaporates. There is no there, only a blur of probabilities. For all our grand cosmic maps and calculations of billions of light years, those measurements rest upon a foundation that is, at its very core, fuzzy and indeterminate. The ruler we use to measure the universe is made of a substance that wavers and dances when we are not looking. Of course, these quantum jitters are unimaginably small, completely negligible when dealing with the vast distances between stars. They are like trying to measure the distance from New York to Los Angeles while accounting for the vibration of individual atoms in your tape measure. The large-scale average is smooth, which is why our models of cosmic expansion work so well, but their existence is a profound philosophical earthquake. They tell us that the smooth, geometric space we assume for all our distance calculations is an approximation, a convenient averaging out of a fundamentally chaotic underlying reality. The emptiness of space is not a simple, featureless void waiting to be crossed. It is a dynamic, structured entity with a complex architecture all its own. This granular foundation suggests that the entire concept of a simple, measurable distance is a macroscopic convenience, a ghost that emerges from a storm of quantum uncertainty. So the next time you look up at the serene, starry sky, remember that the void between those points of light is not a passive stage. It is a vibrant, foaming sea, and our journey across it is far stranger than any map could ever show. This invisible scaffolding of the cosmos weaves itself into the very fabric of distance. Dark matter, a substance that does not emit, absorb, or reflect any light, nonetheless possesses immense gravitational pull. It is the hidden architect of the universe's large-scale structure. Where dark matter clumps together, its gravity draws in ordinary matter, seeding the formation of galaxies and the vast filamentary web that connects them. But this same gravitational influence warps the stage upon which we measure everything. According to Einstein, massive objects curve the space-time around them. A dense knot of dark matter acts like a lens embedded in space, bending the path of any light that passes near it. Imagine looking at a street lamp through the bottom of a wine glass. The light is distorted, its apparent position shifted, creating multiple, warped images. This is precisely what happens on a cosmic scale in a phenomenon called gravitational lensing. A distant galaxy's light on its billion-year journey to us does not travel in a straight line. It is subtly, or sometimes dramatically, bent as it passes through the gravitational fields of invisible dark matter halos and clusters. When we finally observe that galaxy, we are not seeing it where it truly is. We are seeing a mirage, a gravitationally displaced phantom image. Its recorded position on our celestial map is an illusion. This means the distance we calculate to that object, based on where we see it, is inherently wrong. Our most fundamental tool for charting the cosmos, the straight line of sight, is continuously being twisted by an unseen hand. We can even see extreme cases where a single distant galaxy is smeared into a perfect ring of light, or split into multiple, identical copies arrayed around a foreground cluster of galaxies. These beautiful cosmic mirages are direct evidence of dark matter's pervasive grip. By carefully mapping these distortions, we can actually chart the distribution of the invisible dark matter itself. We are drawing a map of the unseen by observing how it warps the scene. Yet this very process introduces a profound uncertainty. Every single measurement of a distant object must now be corrected for the cumulative, subtle lensing effects of all the dark matter along its path. We are forced to model these invisible landscapes, and any error in our model directly translates into an error in our final distance calculation. The cosmos we map is not just a collection of points in a void. It is a dynamic gravitational labyrinth, and every measurement we take is a path through that maze, twisted by forces we can only infer. Our understanding of space is not just relative and expanding, it is optically warped by a ghostly presence that defines the very structures we seek to measure. But perhaps the most dramatic rescaling of the cosmic map occurred before the universe was even a second old. In its very first fleeting instance, the cosmos is thought to have undergone a growth spurt of almost incomprehensible speed, a period known as cosmic inflation. For a sliver of time so brief it defies human imagination, the universe expanded exponentially, doubling in size over and over again, faster than the speed of light itself. This was not an expansion of matter flying through space, but a violent stretching of the fabric of spacetime. In that blink of an eye, a subatomic speck of primordial reality was inflated to a scale larger than our entire observable universe today. This explosive beginning solves a great mystery: why the cosmos appears so remarkably uniform in all directions. The microwave background radiation, that ancient afterglow, has almost exactly the same temperature whether we look left or right. This only makes sense if these vastly separated regions were once in close contact, able to exchange heat and reach a common temperature before being suddenly and catastrophically wrenched apart by inflation. This primordial stretching set the stage for everything to come. It means that 2 points in the sky that appear impossibly distant from each other today, so far that their light has never had time to cross the gulf between them, were once intimate neighbors. The vast separations we measure are not a result of objects slowly drifting apart over time, but are frozen relics of that initial, explosive stretch. The cosmic map we painstakingly assemble is not a chart of initial positions, but a snapshot of a canvas that was already dramatically warped at the moment of its creation. The very geometry of our observable universe, the distribution of galaxies and the voids between them, was imprinted by quantum fluctuations during that inflationary burst, stretched to cosmic proportions. So when we measure the billion light-year gap between two superclusters, we are not measuring a distance that grew steadily. We are reading a fossil, an echo of a violent event that permanently rescaled reality in its first moment of existence, locking in separations that were born from a quantum whisper and amplified to a cosmic shout. Our cosmic rulers are not impartial observers. They are active participants in shaping the reality they measure. Every telescope we build, every instrument we point at the heavens, comes with a set of built-in biases, a unique way of seeing that filters the cosmos before we even begin to interpret it. The data we collect is never a pure, unadulterated signal from the void. It is a signal that has been strained through the technological limitations of our current era. The resolution of our optics, the sensitivity of our detectors, and the specific slice of the electromagnetic spectrum we choose to observe, all of these factors sculpt the final image. They determine what we can see, and just as importantly, what remains hidden. A radio telescope, for example, paints the sky with the brush of long, gentle waves, revealing the sprawling structure of cold hydrogen gas clouds between stars, structures that are completely invisible to an optical telescope. An X-ray observatory, on the other hand, sees only the most violent and energetic processes in the universe, the searing heat around black holes and the remnants of supernova explosions. If you were to map the distance to a galaxy using only its radio emissions, you might pinpoint a different apparent center, a different gravitational anchor, than if you mapped it using the visible light from its stars. The galaxy itself has not changed, but the tool you use to look at it has defined which part of its complex anatomy you are allowed to measure. This instrument-dependent reality means that the cosmic map is not a single, definitive chart. It is a collage, a composite image assembled from dozens of different, specialized perspectives, each with its own blind spots and its own unique revelations. The distances we so confidently assign are not absolute truths discovered in the data. They are conclusions negotiated between the faint whispers of the cosmos and the loud, defining voice of our own machinery. We are not simply reading the universe's story. We are writing it together with our tools, and every new instrument we invent writes a slightly different version. Perhaps the most unsettling question of all is whether the universe is shaped by our own gaze. We have navigated shifting geometry, deceptive light, and stretching space, but now we confront a possibility that challenges the very foundation of science, the idea that our measurements are not just flawed, but fundamentally human-centric. This is the Anthropic Principle. It proposes a simple yet staggering corollary to our existence. The universe we observe must be compatible with the existence of observers like us. The constants of nature, the force of gravity, the very dimensions of space, all seem finely tuned to allow for galaxies, stars, planets, and life. If any of these values were altered by even a minuscule amount, the cosmos would be a barren, empty void, or would have collapsed back on itself instantly. So what does this have to do with distance? Everything. Our entire cosmic distance scale, from parallax to redshift, relies on a stable set of physical laws and constants. The speed of light is a fixed number, the brightness of a supernova follows a predictable curve, the expansion of space has a specific rate. But what if these are not universal truths, but rather local bylaws? This is where the concept of the multiverse emerges. Imagine our entire observable universe, with its hundreds of billions of galaxies stretching out to the cosmic microwave background, is just one bubble in an infinite, frothing sea of other universes. In this vast cosmic foam, each bubble universe could have its own unique set of physical laws. In most, the conditions would be chaotic or sterile, instantly collapsing or flying apart too fast for any structure to form. But in a rare few, by pure statistical chance, the numbers would line up just right to allow for stars and planets, and eventually, beings who can look up and wonder. We, of course, find ourselves in one of those rare, habitable bubbles. This means our cosmic map, with its specific distances and expansion rate, is not the one true map of reality. It is simply the map of our local neighborhood, the only kind of neighborhood where mapmakers could possibly evolve. The vast gulfs between galaxies that we measure might not be a necessary feature of the cosmos, but merely a feature of our particular cosmic habitat, a habitat where such distances are a prerequisite for stable solar systems and long-lived stars. The redshift we see, which tells us a galaxy is billions of light-years away, might be less a universal meter and more a parochial dialect, a way of speaking about space that only makes sense within the walls of our own bubble. The Anthropic Principle does not invalidate our science, but it places a profound philosophical frame around it. It suggests that our quest to measure the absolute distances of the cosmos is like a fish born in a pond trying to measure the entire ocean. It can meticulously chart the depth of its pond, the temperature gradients, and the currents, and from that data, it might infer the properties of water itself. But it can never know that elsewhere there are oceans of brine, of liquid methane, or of substances beyond its imagination. Our cosmic distances, then, are not an illusion of perception or measurement, but perhaps an illusion of perspective. We are not discovering the universe's true scale. We are simply documenting the scale of the one version of reality that allowed for creatures like us to appear and ask the question. The cosmic map we have so carefully charted might be a flatlander's sketch of a much deeper reality. Our entire experience of the universe is confined to three spatial dimensions: length, width, and height. We move through them freely, measuring the distances between stars and galaxies within this familiar framework. But what if this framework is just a slice of something vastly more complex? String theory, a leading candidate for a theory of everything, proposes exactly that. It suggests that the fundamental building blocks of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy called strings. For the mathematics of this theory to work, these strings must vibrate not in 3 dimensions, but in many more, often 10 or 11. So where are these extra dimensions? The theory posits they are compactified or curled up into a space so infinitesimally small that they are completely hidden from our everyday perception. Imagine a garden hose. From a distance, it appears as a single line, a one-dimensional object. But if you were an ant crawling on its surface, you would discover a second dimension, the circular path around its tube-like body. In the same way, every single point in our 3-dimensional space could harbor a hidden, coiled-up geometric shape of extra dimensions, a landscape too small for any instrument to directly probe. This hidden architecture could fundamentally alter the forces that shape our cosmos. Gravity, the force that governs the large-scale structure of the universe, might be uniquely sensitive to these extra dimensions. In our 3-dimensional world, gravity appears incredibly weak compared to the other fundamental forces. But what if gravity's strength is diluted because it is actually spreading out into all these extra dimensions, its influence leaking away into realms we cannot see? The distance between 2 massive objects, as felt by gravity, could be much shorter through a higher dimensional path than it appears along our 3-dimensional grid. The vast gulf between galaxies, which we measure in billions of light-years, might be bridged more directly through these hidden folds in spacetime. Our cosmic map, with its immense, empty voids, would then be a profound illusion. The distances we record would not be the true, multidimensional separations, but merely the 3-dimensional shadows of a much richer geometry. We are like prisoners in a cave, watching the shadows on the wall and mistaking them for the solid objects casting them. Every measurement we take, every calculation of a star's remoteness, is a measurement made by beings trapped in a lower dimensional projection of a reality we are not equipped to fully perceive. The emptiness of space is not empty at all. It is teeming with hidden dimensional folds, and the true path from here to there may be a short cut we have not yet learned to see. This beautiful, consistent picture of an expanding universe has recently developed a crack. Our most precise measurements of the cosmos are now in direct conflict with each other. Astronomers call this the Hubble Tension, and it strikes at the very heart of our cosmic distance ladder. The problem is this: we have 2 primary ways to measure how fast the universe is expanding today. The first method looks at the nearby universe, using Cepheid variable stars and Type Ia supernova as our standard candles. We measure their distances directly and compare them to their redshifts to calculate the expansion rate, a number known as the Hubble constant. This is like measuring the current speed of a car by looking at its tires. The second method looks back to the very early universe, to the cosmic microwave background. By studying the subtle patterns in that ancient light, we can predict how the universe should have expanded over time, and thus what the expansion rate should be right now. This is like calculating the car's current speed by knowing how much fuel was in the tank at the start of the journey and the efficiency of its engine. Both methods are incredibly sophisticated, and both should arrive at the same number, but they do not. The local measurement gives us a faster expansion rate. The early universe measurement gives us a slower one. The difference is small, but it is far larger than any possible margin of error. This is not a minor rounding issue. It is a fundamental disagreement about the current state of the cosmos. Our 2 most trusted cosmic clocks are ticking at different rates. This tension suggests that something is profoundly wrong, either with our measurements or with our model of the universe. Perhaps our standard candles are not as standard as we thought. Maybe there is an unknown, subtle systematic error biasing our observations of nearby stars. Or, and this is the thrilling possibility, perhaps our understanding of physics is incomplete. The discrepancy might be a clue pointing to new kinds of particles, or a strange evolution in the nature of dark energy. It could mean the universe's expansion history is more complex than our simple models can capture. This single number, the Hubble constant, is the linchpin that connects the cosmos we see today with the universe as it was in its infancy. The fact that we cannot pin it down with certainty reveals that our cosmic distance scale, the very foundation of our map, is still unstable. The illusion of a fixed and measurable cosmos deepens, not because space is lying, but because we are still learning how to listen to its true story. This multiplicity of cosmic rulers leads us to a strange but fundamental truth. The distance to a galaxy is not one number, but several, and the answer you get depends entirely on the question you ask. Cosmologists actually work with different definitions of distance, each valid for a specific purpose, and each telling a different part of the story. Two of the most important are proper distance and luminosity distance. Proper distance is the concept that aligns most closely with our earthly intuition. It is the actual physical separation between 2 points at a single, frozen moment in time. Imagine you could stop the expansion of the universe, stretch a hypothetical, indestructible tape measure from Earth to a far-off galaxy, and read the number. That measurement in light years would be the proper distance. It is a straightforward idea, but it is also a phantom because the universe never stops expanding. By the time your tape measure reached the galaxy, the number would already be wrong because new space would have been created in the stretch you just measured. It is a distance that is constantly, relentlessly increasing. Luminosity distance, on the other hand, is what we actually use when we look through a telescope. It is the distance derived from how dim a standard candle appears to be. We see a supernova, we know its true, intrinsic brightness, we measure its faintness, and we plug that into our formula to get a distance. This seems simple, but the expansion of the universe injects a profound deception into this calculation. The light from that supernova is not just spreading out over a vast area, it is also having its energy diluted by the stretching of space itself. As the light waves travel, the space through which they move is expanding, stretching the wavelengths and sapping their energy, making the object appear even dimmer than it should based on simple geometry alone. So when we calculate a luminosity distance, we are getting a number that is inflated by cosmic expansion. It is not the true physical separation, but a distorted measure that combines true distance with the redshift effect. For a very distant object, the luminosity distance will always be larger than the proper distance. Think of it like this. You are trying to judge how far away a car is at night by the brightness of its headlights. But unknown to you, a strange, pervasive fog is also diffusing the light, making it seem even dimmer. Your estimate of the distance would be too great. The cosmic expansion is that fog, so we are left with a bizarre situation. Ask a cosmologist the distance to a galaxy, and they might give you two different answers. The proper distance is the real physical gap, a number that is growing every second. The luminosity distance is an observational artifact, a number warped by the history of expansion during the light's journey. Both are correct, both are useful, but they are not the same. This reveals that our common sense idea of distance, a single, fixed number between 2 points, is a comforting illusion born from our experience in a static, non-expanding world. We evolved to navigate a landscape where the stage does not stretch beneath our feet. In the true, dynamic cosmos, distance is not a simple fact. It is a relationship, a story, and the story changes depending on how you choose to read it. Our cosmic map is not just warped by massive objects, but by the very texture of the cosmos itself. The universe on its grandest scale resembles a vast, three-dimensional spiderweb, a cosmic web of glittering filaments where galaxies cluster like dewdrops. Between these brilliant strands stretch unimaginably vast, dark, and nearly empty voids. This is the true architecture of everything, a lumpy and textured landscape. When light from a distant quasar begins its journey to Earth, it does not fly through a uniform, empty space. It must navigate this complex topography, passing through dense knots of galaxies, along the lighter filaments, and across the profound emptiness of the void. And just as a hiker's path is longer and more arduous over a mountain range than across a flat plain, light's journey is shaped by the gravity of all the matter it passes. As light enters a supercluster, a massive knot in the web, the intense gravity of all that dark matter and those galaxies acts like a valley, bending the light's path and slowing its apparent progress. When it then flies through a vast, empty void where gravity is weaker, it is like climbing out of that valley, able to travel more freely. This gravitational unevenness means that two photons leaving the same distant galaxy at the same instant could arrive at our telescopes at slightly different times, depending on whether their paths traversed a dense filament or skirted the edge of a void. The distance we measure based on the travel time of that light becomes ambiguous. An object that lies behind a particularly dense region of the cosmic web might have its light so delayed that it appears to be farther away than it truly is. Another object whose light had a clearer shot through a less cluttered part of space might seem deceptively close. There is no such thing as a straight line in this curved reality. Our three-dimensional map of the universe is therefore not smooth. It is lumpy, pockmarked by these gravitational hills and valleys. The simple distance between point A and point B is an illusion because there is no empty between. Every line of sight is filled with the invisible, shifting topography of the cosmic web, a landscape that forever twists our perception of here and there. This ancient wall of light, the cosmic microwave background, serves as the ultimate calibration tool for our cosmic map. Think of it as the fundamental blueprint against which every other measurement is checked. By studying the tiny, millionth of a degree temperature variations in this afterglow, these subtle hot and cold spots known as anisotropies, cosmologists can read the story of the universe's infancy. The size and distribution of these spots reveal the precise proportions of the cosmos's ingredients: dark energy, dark matter, and ordinary matter. These numbers are plugged into our model of the universe, and out pops a prediction for the expansion rate and the entire distance scale. It is a cosmic ruler etched into the sky when the universe was a mere 380,000 years old. Yet this pristine ruler is not immune to deception on its long journey to us. As the CMB light travels for over 13 billion years, it does not fly through empty, smooth space. It encounters the very cosmic structures that grew from those initial temperature fluctuations. The gravitational pull of vast dark matter halos and galaxy clusters acts like a lens, subtly bending the path of this ancient light. This gravitational lensing distorts the pattern of hot and cold spots, smearing them and shifting their apparent positions. It is like looking at a blueprint through a warped piece of glass. The lines are still there, but their spacing and sharpness are altered. Furthermore, our own motion through the cosmos creates a Doppler shift in the CMB. We are moving relative to this primordial radiation, which makes one half of the sky appear very slightly warmer and the other half very slightly cooler. This dipole anisotropy is a massive signal that must be carefully subtracted before we can even see the fainter primordial patterns. If our understanding of this motion is imperfect, it introduces a bias from the very start. So when we use the CMB to calibrate the distance to a galaxy a billion light-years away, we are relying on a chain of corrections and assumptions. We are using a ruler that was made in the infant universe, a ruler that has been slightly warped by everything that formed after it, and we are assuming that the universe it describes is the same one we live in today. What if dark energy has evolved over time, changing the expansion rate in a way the CMB cannot predict? The most ancient light we can see provides our most fundamental anchor, yet it ties our entire map of the present to a moment in the deep past, a past that may not tell the whole story of our cosmic now. So where does this leave our most basic intuition, the simple idea of here versus there? We have chased the phantom of distance through warped space, deceptive light, and quantum foam, only to arrive at a philosophical precipice. Perhaps distance is not a fundamental property of the universe at all, but a concept we invented. Our brains are exquisitely tuned for survival on the African savanna, for judging the gap between ourselves and a predator, or the reach to a piece of fruit. We evolved to perceive a world of solid objects separated by measurable voids, and we instinctively project this three-dimensional grid onto the cosmos. But what if the universe does not share our obsession with separation? In a purely relational view of reality, championed by thinkers like Gottfried Leibniz, space is not a container that exists independently. Instead, objects are defined only by their relationships and interactions with each other. The distance between Earth and the Sun only has meaning because of the gravitational and electromagnetic forces acting between them. Without that interaction, the concept of their separation becomes empty, a label without substance. Think of a spider's web. The web itself is not a pre-existing stage. The distances between its strands are defined entirely by the tensions and connections holding it together. If you remove the spider and all the forces, the concept of distance within the web evaporates. In this view, the cosmic web is not just a metaphor, it is a potential description of reality. The vast gulf between two galaxies is not an empty void to be crossed, but a relationship defined by the gravitational influence they exert on one another, however faint, and by the light that has managed to traverse the dynamic expanse between them. The universe may not contain distances, it contains relationships. What we call a billion light-years is merely our clumsy, human-scale translation of a complex, dynamic interaction that has been unfolding for eons. This suggests that our entire quest to measure the cosmos is an attempt to impose a parochial, human-centric framework onto a reality that operates on principles far beyond our innate spatial intuitions. The illusion is not just in our measurements, but in the very question we are asking. We keep seeking an absolute answer for how far, when the cosmos may only understand how connected. Every new window we open onto the cosmos seems to reveal a deeper layer of mystery. The James Webb Space Telescope, peering further into the infrared than ever before, is not just showing us older galaxies, it is showing us galaxies that appear too massive, too mature, to exist so soon after the Big Bang. Their light, stretched by cosmic expansion, tells us they are incredibly far away, a fact that places them in the universe's infancy, yet their developed structure defies our models of how quickly galaxies can form. This creates a paradox. Are our distance measurements wrong, placing these galaxies too far back in time, or is our understanding of cosmic evolution fundamentally flawed? Each crisp new image from Webb refines our cosmic yardstick while simultaneously challenging the very timeline it is meant to measure. In a different realm of physics, gravitational wave observatories are listening to the ripples in spacetime caused by cataclysmic events like colliding black holes. These waves provide a completely independent way to gauge distance. By measuring the amplitude of the spacetime shudder, scientists can calculate how far away the collision occurred, no standard candles required. This new ruler has confirmed the expansion rate measured by some local methods, seemingly deepening the Hubble tension. The cacophony of these cosmic collisions is painting a self-consistent picture that stubbornly disagrees with the picture from the early universe's light. This is the pattern of discovery. Each technological leap shatters an old illusion only to replace it with a new, more profound enigma. The maps drawn by Galileo's telescope were corrected by Hubble's, which are now being refined by Webb's and by gravitational wave detectors. Our current model of the cosmos, with its precise distances and expansion rates, is not a final draft. It is the latest version of a story that is constantly being rewritten, a provisional sketch that feels solid only until the next great instrument reveals the shadows we never knew were there. This vast cosmic web we inhabit might be just a single thread in an infinite tapestry. The Multiverse Hypothesis dares to suggest that our entire universe, with all its hundreds of billions of galaxies, is merely one bubble in a frothing, perhaps infinite, sea of other universes. Each of these cosmic bubbles could operate under a completely different set of physical laws. Some might have stronger gravity, collapsing instantly into a black hole. Others might have weaker nuclear forces, preventing stars from ever igniting. In this staggering panorama, our universe is simply the one where the numbers lined up just right to allow for galaxies, planets, and us. So what does this mean for our concept of distance? If there are other universes, how far away are they? The answer shatters our familiar three-dimensional thinking. The separation between our universe and another one is not a gap you could cross by traveling in a straight line through space. You could fly for 1 trillion years at the speed of light and never reach the border of our own cosmic bubble, let alone enter the next. The distance to another universe is not spatial, it is dimensional. It might involve a transition through hidden, compactified dimensions, a kind of cosmic shortcut through the hyper-realm that lies between bubbles. Another possibility is quantum tunneling, a probabilistic leap where a universe spontaneously transitions into a different state, effectively creating a new bubble adjacent to the old one in a higher dimensional landscape. In this framework, the immense gulfs we measure between superclusters, those billions of light-years of seemingly empty space, become trivial. They are local geography, the streets and parks of our own cosmic neighborhood. The true vastness, the real metropolis, is the multiverse itself, a structure of such scale that the entire span of our observable universe is reduced to a single pixel on an infinite screen. Our most detailed cosmic map, painstakingly assembled over centuries, becomes a charmingly detailed survey of one small island, utterly unaware of the boundless ocean that surrounds it. A future starship, charted by our current maps, would never reach its destination. The illusion of fixed distance is not just a philosophical curiosity, it is a navigational hazard on a cosmic scale. Imagine planning a voyage to a star system 100 light-years away, using a star chart that shows its position as a fixed point. You plot your course, engage your engines, and begin the long journey. But while you travel, space itself is stretching. The star you are aiming for is not sitting still at the end of a static road. It is receding from you as the fabric of the cosmos expands. Over a century of travel, that expansion, though minuscule on such a relatively small scale, would accumulate. You would arrive not at your target, but in an empty patch of space where the star used to be, having been carried off course by the silent, relentless growth of the universe itself. This means any serious plan for interstellar travel must treat the cosmos not as a fixed map, but as a dynamic, flowing river. Our navigation computers would need to be more than just calculators. They would need to be cosmic predictors, constantly updating their course based on real-time measurements of the universe's expansion and the peculiar motions of stars. They would not just aim for where a star is, but for where it will be when we finally arrive, a point that is constantly shifting. The very concept of a destination becomes a moving target. This is the profound practical consequence of our cosmic illusion. To journey between the stars, we must first accept that the void is not empty and the paths are not straight. We must learn to sail not on a still ocean, but on a rising tide, navigating a universe that refuses to hold still for its travelers. Our cosmic journey ends not with a final number, but with a humbling realization. Every distance we measure is a story told by a flawed messenger, a tale filtered through expanding space, warped by gravity, and frozen in relativistic time. From the simple triangles of the ancient Greeks to the ghostly push of dark energy, each new ruler we fashioned revealed not a simpler truth, but a deeper layer of cosmic deception. We built a ladder to the heavens only to find that every rung was made of shifting sand. The universe resists our desire for a single, stable map. It is a fluid, dynamic entity where here and there are temporary relationships, not fixed coordinates. Our most sophisticated charts are not discoveries of absolute reality, but merely the best possible translations we can manage from a language of space-time we are only beginning to learn. This is not a failure of science, but its greatest triumph, a constant reminder that the cosmos is far stranger, more wondrous, and more mysterious than our earthly intuitions could ever allow. So the next time you look up at the starry void, see it not as a static picture, but as a living, breathing illusion, a grand invitation to forever question what you think you know. What cosmic deception surprised you the most? Let us know in the comments, and if you are ready for more journeys into the unknown, subscribe for our next exploration into the mystery